and turns out this is a family leaf. So graph G has a perfect matching if and only if the number of odd components in G minus S is less than equal to the cardinality of S for every subset of the vertices. Right? That is Tutte's theorem from 1947. And so now using this, the corresponding decision problem is both in NP and in co-NP. You can easily convince somebody that a graph does not have a perfect matching. Easily in the sense that there is a certificate that I can just show to you. Of course, the question is how do you find that certificate? That was done by Edmonds in 1965. If you don't know this algorithm, it doesn't matter. I teach it in my other course, LPCO. I don't teach this chemistry. So Edmonds basically showed that the problem also belongs to P, and because of this theorem, the problem belongs to NP intersection co-NP. Right, and if you have not taken a full course in algorithms, is that correct? Or in theory of computing, you may not know the formal definition of these, but that doesn't really matter. The only definition I need to know is intuitively, if I give you the certificate, you can check it quickly. But quickly really means polynomial time on deterministic machine. Don't worry about that too much. I don't need that technicality. But intuitively, I hope it's clear what these things mean. Right? And so this was already in 1947. Depending on how you phrase the decision problem, the point that belongs to the intersection of these two classes. But it took another 18 years to get a polynomial time algorithm. Okay. So you can check whether a graph has a perfect matching or not efficiently. Okay. So we could have stopped there and we could have said, okay, we know everything about perfect matchings. So, but that is not what we did. People ask more questions. Right? So I'll give examples of such questions. This is just a 0-1 question. Is there a perfect matching or is there no perfect matching? But you can ask, can you count the number of perfect matchings? This turns out to be very difficult. This was shown to be valid in 1979. Showed that one cannot count the number of perfect matchings in a graph efficiently unless P equals NP. Not NP unless P equals NP. Okay. So, in fact, they showed something stronger called Sharpie complete, but even I don't know the definition of Sharpie complete, so I'll say probably some social numbers. Anyways, no need for that because oh, that was only for bipartite? Or even for bipartite? Even for bipartite, yeah. This is actually an interesting point. Even in the case of bipartite graphs, still this is not NP unless P equals NP. Which is interesting because for a lot of problems in matching theory, if you restrict yourself to bipartite graphs, it is much easier. Even if you ask about these kinds of questions, Hall's theorem was known much more before Tutte's theorem. And finding a perfect matching in a bipartite graph or reporting that one doesn't exist was known much earlier before Tutte's theorem. But yeah, in the case of counting, bipartite doesn't make it easier. Okay, so that's one problem. And let's talk about this problem briefly. Right, so most of you probably know this standard example. If I want to count the number of perfect matchings in this graph, For example, there is an edge that is not in any perfect matching. Right? Everybody sees that edge. This edge is not in any perfect matching. So I might as well throw away that edge. And the number of perfect matchings will not change, right? If I throw away this edge, the number of perfect matchings is still the same because that edge was not in any perfect matching. So now if I count, now what I have in this example, I threw away one edge and I have now two components, and in these components every edge belongs to some perfect matching. So if I can count the number of perfect matches in these components, then I just multiply them 2 times 3 and I get 6. That's the number of perfect matchings in the original graph with that edge. So that brings us to the definition of a matching code graph. It's a connected graph and each edge belongs to some perfect matching. And of course, there's one problem, there is K1. K1 is also matching covered according to this, which is useless. So we will say at least one edge. Oh, by the way, throughout this course, we allow multiple edges, also known as parallel edges. We don't allow loops, just like module 5 of STD. Loops make no sense in matching theory, so we don't allow. So the point is, if I can count the number of perfect matchings for matching covered graphs, then I can count the number of perfect matchings for all graphs. Yeah, you all agree? I will just find out all the unmatchable edges, those that are not in any perfect matching. I will throw them away. Now I will get a bunch of components. Every component is matching covered, assuming that the original graph had a perfect matching to begin with. Right? Now I will just use my algorithm for matching covered graphs if I have one. Then I can count the number of perfect matchings in all graphs. So this is one example where you can restrict yourself to matching covered graphs. There is no point in considering those useless edges. Okay. So definition. We will use the term matchable in 2 different ways. Matchable graph that has a perfect match. And matchable edge of a graph is an edge that belongs to some perfect matching. If an edge is not matchable, then otherwise either it is matchable, otherwise it is unmatchable. This was not the original word. I am choosing basically all the terminology from Lucchesi and Murty. This was not the original word they used. Cláudio, Lucchesi, Murty, they worked in matching word graphs for many years. They used another word called admissible and inadmissible. Turns out the reviewer of their book, Charles Little, who was also the external examiner for my PhD thesis, he is very picky about words. He was like, why are you using inadmissible, admissible? He kind of argued with them a lot. No, you should use another word, use matchable and matchable. And finally the authors were like, okay fine, we'll use matchable and matchable. So we'll use the word matchable in 2 different ways. Yeah. So for an example, in this graph, this is the only every other edge in this graph will match. Okay. Alright. So let's look at another problem, but again I would like to convince you that you can restrict yourself to matching cover graphs. So matchings have been studied extensively, not just perfect matchings but matchings in general have been studied extensively from an algorithmic point of view, combinatorial optimization, which is sort of a cousin of algorithms in some sense. From a graph theoretic point of view, they have also been studied a lot in things like economics, statistical mechanics, which is a branch of physics, etc. etc. And of course, the enumerative combinatorics people have also studied matchings and perfect matchings and continue to study them. So there is a lot of literature. One of the areas, this combinatorial optimization, you study various polytopes. So you consider various polytopes, and one such polytope is the perfect matching polytope. Depending on how much time we have, we may actually cover some topics related to the perfect matching polytope. So what is a perfect matching polytope? Let me just give you a quick example. Here is, as you know, one of my favorite graphs, the triangular prism. How many perfect matches does it have? I'll give you a hint. Some of you already know this. I want you to count the number of perfect matchings in this graph, and I want you to pay attention to this cut. If you pay attention to this cut, then counting the number of perfect matchings is very easy. Not the ones who already used. Six. Try to find out the six. Three. Okay, write down all the three. And then see if you are missing any. And see if you are overcounting any. You both have given bounds. One is a lower bound, one is an upper bound. How many? Four, right? Yeah, exactly. So the main point is that for any perfect matching, the intersection with this cut, first of all, it has to be odd, because this cut is an odd cut. Odd number of vertices on the left side, odd on the right side. So the intersection has to be either 1 or 3. If you take the intersection to be 3, then of course you get one perfect matching. And if you take the intersection to be 1, then depending on which one, you get 3 different perfect matchings. Because once you choose an edge in the cut, and you don't choose the other 2, the remaining 2 are already determined. So you get 3 of the type 1 and 1 of the type 3. That adds up to 4. Yeah? Okay. So now what you can do is, you can take any perfect matching of this graph, and you can think of it as a vector. I will put 1 on the edges that are chosen and I will put 0 everywhere else. So it is a vector n n is the number of edges. You can think of each perfect matching as a vector in Rn. This is similar to module 1 in STT, where you think of cycles and even subgraphs or bonds and cuts as vectors, and then you do a bunch of fancy things. So in the same sense, you can think of these as vectors. So you have a bunch of 0, 1 vectors, the number of perfect matchings, that many vectors you have. And now what you can do is you can take the convex hull of all these vectors. The convex hull is the smallest convex body in that space that contains all of the vectors. And the fact that it is unique needs a proof, but that's a standard polyhedral combinatorics exercise. So you can consider so what is the perfect matching polytope? It is the convex hull of all perfect matchings of the graph G viewed as 0, 1 vectors. Okay. So in the case of this graph, you have exactly 4 perfect matchings. So you get 4 vectors, and you are looking at the convex hull of these 4 vectors. That is in R9 because you have 9 edges in this graph. Okay. And now you can ask various questions about this polytope. So people have asked a lot of questions regarding this polytope, and better understanding of this polytope can potentially help you in optimizing over the set of perfect matchings. So one of the famous problems with perfect matchings is to find the minimum cost perfect matching in a graph, where now you have every edge is a cost, and the cost of a perfect matching is simply the sum of the cost of the edges of that perfect matching. And now you have to find a minimum cost perfect matching. So how do you solve this problem? Well, basically you are optimizing over a polytope. In this polytope, you are trying to find what is called an extreme point of the polytope, which attains the minimum cost. Right? So anyways, I don't want to go into those optimization things, but this is a very well studied geometric object. And now let's ask the question, what is the contribution of this edge? If I consider the perfect matching polytope of this graph, what is the contribution of this edge? In all the vectors it is 0. It is simply adding an extra padding bit to your vectors. Right? In the convex hull also, because you are taking convex combinations, it will again always be 0. So it has no contribution. So you might as well throw away this edge, and you might as well study the perfect matching polytope of these graphs. Right? And I think there is a term they call direct sum. The direct sum, the perfect matching polytope of the original graph is just the perfect matching polytope of this graph, and direct sum with the perfect matching polytope of this graph. So just use this. Right? So even if you want to understand the perfect matching polytope, you can restrict yourself to matching cover graphs. Yeah.
So when you are assigned some weight to edges, when you are taking the vector, then instead of 0, 1, you are considering that weight.
Oh no. So if you have, if you go back to this minimum cost perfect matching polytope, there is a weight on the edges, right? But you are still trying to find a perfect matching of minimum weight. So the perfect matchings are still going to be 0, 1 vectors. Just that the cost of the perfect matching, instead of adding all of the ones, you will add up 1 times cost of that edge plus 1 times cost of the other edge and so on. So your vectors are still the 0, 1 vectors. It is just the cost of the vector is encoded in the cost vector. So there is a cost vector, and you just multiply that with your perfect matching vector.
Yeah, scalar product.
Exactly. Right? So the vectors are still 0, 1 vectors. My main point was to convey that if you want to understand the perfect matching polytope, the geometric object, you again can restrict yourself to matching coordinates. You don't need to consider these edges that are not in any perfect matching. They are useless. Right? That's all I'm trying to do. And the same argument can be made for other geometric objects that arise from the perfect matchings. I'll give you one quick example. Another geometric object that people have studied. So this one I will relate to coloring three regular graphs. You know by SGT that every three regular graph G its H chromatic number is either 3 or 4. Yeah. Essentially, Gupta theorem, although in the Gupta theorem you typically have to put simple three regular graph. But in the case of three regular, you don't even need simple. You can actually prove this using Brooks theorem, which is from the coloring module of SGT. So this is also a true statement. You don't need simple. What does it mean for a three regular graph to be 3H colored? Can you phrase it in terms of perfect matchings? If I say that a three regular graph is 3H colorable, can you phrase this in terms of perfect matchings?
It has three perfect matchings.
It has three adjective perfect matchings. You need some adjective. You're on the right track. It has three perfect matchings. Disjoint.
Yeah, disjoint.
Three disjoint perfect matchings. Yeah. So 3 means that the graph G has three disjoint perfect matchings. In fact, to make it even clearer, because you can interpret this in two different ways, I will call it pairwise disjoint. Yeah. So having three pairwise disjoint perfect matchings, can you now phrase that in terms of these vectors? I want to now phrase this. I want to now find another equivalent way of thinking of this. These are equivalent. I want to think of this in terms of these vectors.
They are going to orthogonal.
Hmm?
They are going to orthogonal. We corresponding to these perfect matches, if we take the vector, they are going to be orthogonal.
You mean any two of them will be orthogonal to each other. The dot product will be 0. Yes, because they are disjoint, you will always get 0. That's right. That's one way of looking at it. Yes. Okay. Any other ways of looking at it?
Independent. Orthogonals are independent.
Right. Okay, I will give you a hint in what direction I am thinking. So we looked at the perfect matching polynomial, which is basically the convex hull, which basically means you take all convex combinations. So can you now think of it in terms of combinations?
And the coefficient is going to come from real number.
Right, okay. You can allow all real coefficients. Then what vector will you get? Any n subset, or do you want a specific n subset?
Three-dimensional subspace of R.
Okay, I'll give you a hint. I want the all ones vector. I want to write something like this.
So just add them.
The all ones vector can be written in some way.
If we add all three, then
The all ones vector can be written as a sum of three perfect matchings. But what coefficients are we going to allow?
One by three, 1 by
If you do 1 by 3, 1 by 3,
One.
yeah, so the, can I just say that I can write it as non-negative integer linear combination of perfect matches? Is this a correct statement? The all ones vector can be written as a non-negative integer linear combination of perfect matches.
Why not just you are adding all three?
Right. So you can add 3 perfect matchings, add the corresponding vectors, and you'll get the all one vectors. Right. But I can also relax it, and I can say I can choose any non-negative integer linear integers. I'm basically looking at a larger space. And in this larger space, if the all ones vector is there, then the graph is 3H curvable. Otherwise, it is not 3H curvable. So think about that. Right? So what you can do is you can take all your perfect matchings, these are 0, 1 vectors, and you can consider the entire space. This is the set of all non-negative integer linear combinations of perfect matchings of the graph. And I claim that if I can check for membership of the all ones vector, if you give me a polynomial time algorithm to check membership of the all ones vector, I can just check if it belongs here, the graph is 3H curvable. If it does not belong here, the graph is not 3H curvable. Is that a correct statement? So, yeah. So my point is, if I can check for membership of all ones vector in this set, then I can basically say whether the graph is 3H curvable or not. If it is 3H curvable, then the all ones vector should be in this set.
This is clear.
Otherwise, it should not be in this.
Integer linear combination, so converse will also.
So one side is clear.
One side is clear. For converse, you are taking non-negative integer linear combinations. You can't have fractions to adjust the ones. You will need to have one somewhere.
Correct.
Yeah, the non-negative is actually important. If you drop the non-negative, then this is not very clear. In fact, it is a false statement. I'll give you an exercise that I don't know the answer to myself. Let's see. Peterson graph is not 3H curvable. In the case of the Peterson graph, maybe I should give you another graph.
This.
Yeah, this is definitely 3H curvable. So then what I want to do is, so here is what I want to do. So it turns out this non-negative is very important. If you remove non-negative, this set actually changes. This set actually becomes bigger. Of course, intuitively it should become bigger, but does it actually become bigger is not entirely clear. So it turns out this non-negative is actually very important. If you remove non-negative, you get another geometric object called the matching lattice. So what is a matching lattice? This is my third point. The matching lattice it's basically this, but I will drop non-negative. Yeah. This is a set of all integer linear combinations of I decided to draw differently now I'm doing the price. Okay. This is not the Peterson graph. What I've done is I've blown up one vertex into a triangle. An operation that Cláudio is extremely familiar with. So this is a nice graph. It is not 3H colorable. If this were 3H colorable, you can easily prove that the Peterson graph is also 3H colorable. You just have to pay attention to this cut. Okay? So this is not 3H colorable. Therefore, according to our discussion, the all ones vector cannot be written as a non-negative integer linear combination of perfect matches. Yeah, for this graph. However, if you relax your set and you consider integer linear combinations, then you can do it. The exercise is, for this graph, show that the all ones vector can be written as an integer linear combination of perfect functions. I don't know how to do it, so when you find out, let me know. I know it is true because I know some theorem, but I have not found out this example. Yeah. So why am I telling you this story? So this is a major open problem. Deciding whether this is 3 or 4, it is actually NP complete because of a result of Hollier. So Hollier is the one who showed that deciding whether a graph is 3H colorable, cubic graph, 3 regular graph, whether it is 3H colorable or not, is NP complete. I will keep using the word cubic for 3 regular. But people were still interested in figuring out whether we can get some handle on this. So what they did is, it is common that when you are stuck in a situation like this, you look at some geometric object, like the set of all non-negative integer linear combinations. If you can characterize this set, this geometric feature, then if you have a complete characterization, you should be able to check whether the all ones vector belongs to the set or it does not belong to the set. If you can do that, then you would have answered this question. But of course, people were, because this problem is NP complete, there is not much hope. So what people often do is they look at a larger set and they try to characterize that larger set. So the larger set is matching lattice. This is a larger set in theory. Yeah. And the question is, can we characterize this set? Given any matching, given any graph that has a perfect matching, can we get a handle on this set, the matching lattice? In particular, can we check whether the all ones vector belongs to this set or does it not belong to this? This turns out it is a solved problem. This was one of the biggest breakthroughs in matching theory due to Lomas, 1987. Lomas. If we have time, we may actually discuss this in the course. I am really hoping to discuss this. I just don't know how much time we will have. But what I want to convince you once again, just like the perfect matching polytope, the edges that are not in any perfect matching, they are useless. You can throw them away. So therefore, you can restrict yourself to matching over graphs. Okay. So we have seen 3 examples, counting number of perfect matchings. And basically any geometric object that depends on the set of perfect matchings. That could be the polytope, that could be the matching lattice, that could be this set where you impose non-negativity. For all of these sets, you don't need to worry about the unmatchable edges. They are useless. Yeah? And that is one big reason. That is basically the main reason why we study matching graphs. Right? And of course, if you study something long enough, then you just get interested in it and then you don't even need a justification. So that is my situation. Right? But anyway, since this is the first lecture, I thought I will give you some justification as to why one should study matching monographs. Okay. Questions, concerns? Yes. Oh, Loas gave a